Hey everyone, welcome back to the channel. Today, we're diving into something every data professional should master: data modeling architecture. Whether you're a data engineer, analyst, or architect, understanding this is a must.
Data is the backbone of modern applications, and how we model that data makes all the difference between a system that scales and one that struggles. So, what exactly is data modeling architecture? Think of it as the blueprint for how your data will be structured, stored, and retrieved. It involves designing models that guide how data flows from business needs to actual database structures. There are three key layers in any data modeling architecture. First, we have the conceptual data model. This is the high-level design. Like an architect's sketch, it focuses on what data is important, not how it's stored. Here, we define the entities, their relationships, and the rules, without worrying about technical details. Next, we move into the logical data model. Now we're getting more technical. We define tables, columns, data types, and normalization, still independent of any specific database engine. And finally, we build the physical data model. This is where it gets real. We translate everything into actual SQL tables, indexes, constraints, and performance-tuned structures specific to a database system. Understanding this layered approach helps teams collaborate better, from business analysts to data engineers to developers. So, stay tuned. In the upcoming videos, we'll dive deeper into each model and explore best practices, tools, and real-world use cases. In this section, we'll explore the three core types of data models that form the foundation of any data architecture. Keycap 1: Conceptual Data Model. This is the big picture view. It's used by business stakeholders and data architects to define the what of the data. What entities exist? What relationships connect them? What are the key business rules? No technical details here, just a high-level structure that helps align everyone's understanding. Example: entities like customer, product, and order, with lines showing their relationships. Keycap 2: Logical Data Model. Now we start to bridge business and tech. The logical model defines tables, attributes, or fields, and their data types, primary and foreign keys. Normalization for eliminating redundancy, but it's still database independent. It's like drafting a floor plan without worrying about building materials. This is where data architects and engineers collaborate closely. Keycap 3: Physical Data Model. Here's where the rubber meets the road. The physical model maps the logical model to a specific database platform, like PostgreSQL, MySQL, or Snowflake. It includes exact column types, like varchar 255, int, date, indexes and partitions for performance, security constraints, storage and hardware considerations. This model is used directly to build and deploy the database. Each model serves a different purpose, but together, they ensure consistency, scalability, and alignment across teams. Understanding the difference between these three models is critical for building robust data systems. Welcome to the next section of our data modeling architecture series: Key Components of Data Models. Understanding the building blocks of data models is essential for designing efficient and scalable databases. Let's break it down. 1. Entities and attributes. At the core of any data model are entities, the objects or things you want to store information about. Think of entities like employee, student, or product. Each entity has attributes, which are the pieces of information you want to track. For example, an employee might have attributes like employee ID, name, and designation. 2. Relationships. Relationships define how entities are connected to each other. There are three main types: one-to-one. One record in entity A is linked to one record in entity B. Example: each employee has one unique ID card. One-to-many. One record in entity A can be linked to multiple records in entity B. Example: one department can have many employees. Many-to-many. Multiple records in entity A can relate to multiple records in entity B. Example: students can enroll in multiple courses, and each course can have many students. 3. Primary and foreign keys. A primary key uniquely identifies each record in a table. It ensures that there are no duplicates. A foreign key is a field in one table that links to the primary key in another. It helps maintain referential integrity between tables and defines relationships. 4. Normalization and denormalization. Normalization is the process of organizing data to reduce redundancy and improve data integrity. It involves splitting data into related tables and using foreign keys to link them. On the other hand, denormalization is the process of combining tables to reduce the number of joins and improve read performance, commonly used in analytics. And there you have it: entities, relationships, keys, and the balance between normalization and denormalization. These are the key components that form the foundation of every well-structured data model. In the world of data modeling, choosing the right approach can shape the success of your data architecture. Two foundational strategies are the top-down and bottom-up approaches. Let's start with the top-down approach. In this method, modeling begins at a high level, usually starting with business requirements and conceptual models. It's all about understanding what data the organization needs, and why. From this big picture view, we break it down into logical and then physical models. The top-down approach is ideal for new systems or when the goal is to align data with business processes from the start. It ensures consistency, avoids redundancy, and aligns well with strategic planning. Now, let's look at the bottom-up approach. This approach begins with the actual data sources, the existing tables, files, and datasets. From these granular components, we gradually integrate them to form logical and eventually conceptual models. It's a practical method, often used when dealing with legacy systems, or when reverse engineering databases. The bottom-up approach provides a realistic view of what data already exists and how it behaves. Comparison time. Top-down is driven by business goals. It's structured and ideal for fresh designs. Bottom-up is data-driven. It's reactive, faster to implement, and grounded in existing infrastructure. In modern data architecture, teams often blend both approaches, leveraging the business-driven clarity of top-down with the practical insights of bottom-up. One of the most fundamental tools in data modeling is the Entity Relationship Diagram, or diagram. Introduced by Peter Chen in the 1970s, it remains a cornerstone in how we visualize and design databases. So, what exactly is an diagram? An diagram is a visual representation of data, showing entities, their attributes, and the relationships between them. Think of it as a blueprint of your data ecosystem, where every table, field, and relationship is mapped out for clarity and precision. Let's break down the core components. Entities. These represent real-world objects or concepts, like customer, product, or order. Each entity becomes a table in the database. Attributes. These are the properties or details of an entity, like customer name, email, or order date. They form the columns of the table. Relationships. These define how entities are connected. For example, a customer places an order, or a student enrolls in a course. Types of relationships. One-to-one. Each entity instance relates to only one other. One-to-many. One entity relates to many others. The most common type. Many-to-many. Multiple entities on both sides relate to each other, often requiring a junction table. Why use diagrams? They simplify communication between developers, analysts, and business stakeholders. They help identify data requirements and constraints early in the design phase. They act as a visual contract for how data should be structured and interact. Whether you're designing a brand new database or optimizing an existing one, diagrams provide the clarity and structure needed for success. Next up, we have UML for data modeling. UML, or Unified Modeling Language, is a standardized way to visualize the design of a system. In the context of data modeling, UML is used to describe data structures and the relationships between them. It provides a powerful way to create detailed and structured diagrams that help you understand and design your system's data architecture. UML diagrams include various types, but for data modeling, we primarily focus on class diagrams and object diagrams. Class diagrams. Class diagrams are the most commonly used in data modeling. They depict the system's objects and their relationships. In this diagram, classes represent entities, and the attributes of these classes represent the properties or characteristics of the data. The lines between classes represent relationships, like one-to-one, one-to-many, or many-to-many. Object diagrams. Object diagrams are used to represent instances of classes. They provide a snapshot of the system at a particular moment in time, showing how the objects relate and their values. Advantages of using UML. Clarity. UML diagrams are easy to read and understand, making them a valuable communication tool for both developers and non-technical stakeholders. Standardization. Being a widely accepted standard, UML allows consistency in the way data structures are represented. Flexibility. UML is adaptable to various types of systems and projects, whether you're modeling a small database or a large enterprise application. By leveraging UML for data modeling, you ensure that your design is structured, scalable, and easily understandable, allowing teams to collaborate more effectively. Now, let's move on to another critical technique in data modeling: star schema versus Snowflake schema. These two schemas are widely used in data warehousing and reporting to organize and optimize data for analytical querying. Star schema. The star schema is characterized by a simple, straightforward structure. It consists of a central fact table, which holds quantitative data like sales figures or transaction amounts, surrounded by dimension tables that describe the context of the data, such as product names, customer details, or time periods. What makes the star schema so attractive is its simplicity and ease of querying. The relationships between the fact and dimension tables are typically one-to-many, and since the dimension tables are denormalized, it reduces the number of joins required during querying, making it faster for read operations. However, this denormalization can lead to data redundancy. Snowflake schema. In contrast, the Snowflake schema is a more complex variation of the star schema. While it still has a fact table in the center, the dimension tables are normalized into multiple related tables. This normalization reduces data redundancy but increases the complexity of queries, as more joins are required. The Snowflake schema is useful for organizations that require strict data integrity and prefer to store data in a more normalized format. However, the performance of queries may suffer due to the need for multiple joins. Key differences. Simplicity. The star schema is simpler and more straightforward, while the Snowflake schema involves a more complex structure. Performance. Star schema generally performs better for queries due to fewer joins, while Snowflake schema may require more joins, potentially slowing down performance. Data redundancy. The star schema has more data redundancy due to denormalization, whereas the Snowflake schema reduces redundancy through normalization. In conclusion, the choice between star schema and Snowflake schema depends on your organization's specific needs. If query performance and simplicity are key, the star schema is ideal. However, if data integrity and storage efficiency are a priority, the Snowflake schema may be the better choice. In this section, we will explore the various tools available for data modeling. Data modeling is made easier with specialized tools that assist in designing, visualizing, and maintaining databases effectively. Whether you're building a conceptual model or preparing a database schema for production, using the right tool can make the process much smoother. Popular tools. There are several popular tools used in the industry for data modeling. Some of the most recognized ones include ERwin, a comprehensive data modeling tool used by enterprises for both physical and logical data models. It helps to design, analyze, and maintain databases efficiently. Lucidchart, a cloud-based diagramming tool that provides easy-to-use templates for diagrams, flowcharts, and UML diagrams. It supports real-time collaboration, making it ideal for team-based data modeling. Diagram.io, a simple and free tool for creating database diagrams. It allows you to quickly design, share, and document your data models in a straightforward, visual format. These tools come with a variety of features, such as automated schema generation, reverse engineering, and database visualization, making them indispensable for modern data modeling. Open source versus enterprise tools. When it comes to choosing a tool, you may encounter two broad categories: open source and enterprise tools. Open source tools are free to use and often come with community-driven development. Tools like DB Designer and PG Modeler offer a solid set of features for database design without the hefty price tag. They may lack some advanced functionality found in enterprise tools, but they are sufficient for many organizations. Enterprise tools like ERwin and Microsoft SQL Server Management Studio offer advanced features like integrated version control, robust reporting, and support for large-scale database management. These tools usually come with a subscription cost, but they are equipped with features needed by large organizations managing complex databases. Collaborative modeling tools. Collaborative modeling tools allow teams to work together in real time. In today's agile and collaborative development environments, the ability to design and update data models as a team is critical. Tools like Lucidchart and Draw.io allow multiple team members to collaborate on the same data model simultaneously, adding layers of efficiency to the design process. Additionally, some enterprise tools, such as ERwin Data Modeler, come with collaboration features built into their workflows, allowing designers, developers, and stakeholders to view and provide input on the model. Effective data modeling is crucial for building reliable, scalable, and efficient systems. In this section, we'll explore some of the key best practices that help create robust data models. 1. Naming conventions. Consistency is the foundation of effective data modeling. Establishing clear and standardized naming conventions for tables, columns, and relationships improves the readability of your data model. A good naming convention ensures that developers, data analysts, and business users can easily understand the model and maintain it over time. For example, always use singular names for entities like customer instead of customers, and ensure that column names are descriptive and follow a consistent format. 2. Avoiding redundancy. Redundancy in data models can lead to inefficiencies, inconsistencies, and difficulties in maintaining the system. One of the goals of data modeling is to eliminate unnecessary duplication of data. This can be achieved by adhering to the principles of normalization. However, it's also essential to balance normalization with performance considerations. Sometimes, denormalization may be necessary for performance optimization, but avoid excessive duplication. 3. Keeping scalability and performance in mind. A good data model should be flexible enough to handle growth, both in terms of data volume and complexity. When designing your data model, keep scalability in mind. Ensure it can grow without significant redesign. Performance is another critical factor. Avoid overly complex joins or data retrieval paths that could slow down queries. For example, consider indexing frequently queried columns, and optimize relationships for efficient querying. 4. Versioning models. As business requirements change and systems evolve, so should your data models. It's important to version control your data models, just like you would with code. Versioning allows you to track changes, roll back to previous states, and maintain consistency as the model evolves. Tools like Git or specialized data model versioning tools can help you manage changes over time and ensure that your team works with the most up-to-date version of the data model. Welcome to the next chapter, data modeling in cloud architectures, a critical area as businesses continue migrating to the cloud. Let's start with the differences in cloud-native modeling. Traditional data modeling focused heavily on physical infrastructure and tightly coupled databases. In contrast, cloud-native modeling embraces flexibility, scalability, and distributed data. Cloud systems are built to scale horizontally, which affects how we design our schemas and choose data storage systems. In the cloud, your data models need to accommodate elastic compute, distributed storage, and event-driven architecture. This means avoiding rigid structures and leaning more toward denormalized, performant data layouts. Now let's talk about modeling for data lakes and warehouses like BigQuery, Snowflake, and Amazon Redshift. These modern warehouses are optimized for analytical workloads. In such systems, your models should favor denormalization, star or Snowflake schemas, and partitioning strategies. Unlike OLTP databases, these systems thrive when you reduce joins and flatten your data for faster querying. BigQuery, for example, performs best with nested, repeated fields. Snowflake supports semi-structured data and time travel, and Redshift uses distribution keys and sort keys to optimize query performance. Finally, the ongoing debate, NoSQL versus SQL modeling. SQL models focus on structured, relational data with well-defined schemas, supporting powerful ACID-compliant operations. ideal for transactional systems. Noscal, on the other hand, is schema flexible, distributed, and suitable for unstructured or rapidly changing data. It shines in use cases like IoT, real-time analytics, and content management. While SQL modeling encourages normalization and strong constraints, Noscal modeling is about access patterns, redundancy for performance, and denormalization. In cloud-first architectures, choosing between SQL and Noscal, or using both in a polyglot strategy, can determine the success of your data system. Welcome to one of the most important topics, challenges in data modeling. While data modeling is foundational for good architecture, it's not without its roadblocks. Let's dive into some key challenges modern teams face. Evolving business needs. Business requirements don't stay still. They evolve, sometimes rapidly. What worked for your application 6 months ago might be completely outdated today. This constant evolution demands flexible, adaptable models. Rigid models struggle to keep up. Over-engineering early on or underestimating future needs can lead to painful rework. The key: build with agility. Create modular, extensible schemas that grow with your business. Handling unstructured data. Today's data doesn't always fit neatly into rows and columns. We have logs, images, social posts, JSON, PDFs. The list goes on. Modeling this kind of unstructured data is complex. Do you store it as is in blob storage or use schema on read techniques like in data lakes? Do you enrich and index it for querying? You often need a hybrid approach. Structured models for known entities, and schema-less or flexible stores for unstructured or semi-structured content. Data model drift in agile teams. Agile development is great for building fast, but it can cause data model drift, where the implementation diverges from the original model over time. Multiple developers making rapid schema changes, no documentation updates, and lack of version control can create confusion, bugs, and data integrity issues. Combat this with strong communication, automated schema versioning, and regular reviews of your data models. Data modeling is a discipline of balance, between structure and flexibility, between speed and stability. Welcome to the final section, data modeling in real-world projects. Let's connect theory with practice by exploring how data modeling shapes critical domains like e-commerce, healthcare, and banking. E-commerce scenario. In an e-commerce platform, your data model needs to handle a wide array of entities, users, products, orders, carts, payments, inventory, and all their relationships. Modeling decisions here impact performance, optimizing product and order queries using proper indexing and denormalization. Scalability, designing for spikes during sales like Black Friday with sharded schemas or distributed databases. Analytics, structuring events and customer data to power recommendation engines and sales insights. A poor model might result in slow page loads, lost orders, or inaccurate reports. Healthcare scenario. In healthcare, precision is everything. Data models must capture patients, appointments, diagnosis, lab reports, and HIPAA-compliant audit logs. A good model supports traceability, complete and accurate medical histories, security and privacy, fine-grained access control with encrypted fields. Compliance, designing with healthcare regulations in mind, for example, HL7 or FHIR standards. Real-time systems, like ICU monitors, may rely on Noscal for speed, while EMRs often stick to traditional relational databases. Banking scenario. In banking, every transaction matters. The model should represent customers, accounts, transactions, credit scores, fraud detection signals, and more. Key concerns include data integrity, using ACID-compliant models for financial accuracy, fraud detection, designing time series or graph models to track anomalous patterns, audits and compliance, ensuring all changes are traceable for regulatory review. Even a minor modeling oversight could result in legal penalties or financial loss. Impact of modeling on performance and analytics. In all of these cases, the structure of your data model directly affects query performance, storage efficiency, ease of integrating new features, quality of analytics. The best data models aren't just technically sound, they are purpose-built for the business context they serve. And there you have it. We've just taken a deep dive into the world of data modeling architecture, from foundational concepts to real-world applications. But remember, data modeling isn't just a technical skill. It's a bridge between business needs and technical execution. It helps teams design systems that are scalable, performant, and insightful. So whether you're a data engineer, architect, analyst, or just starting out in tech, mastering data modeling will elevate your game to the next level. If you found this video helpful, don't forget to like, share with your team, subscribe for more in-depth content on data, architecture, and engineering excellence, and drop a comment if you want to see case studies or tool walkthroughs in future videos. Thanks for watching, and until next time, keep modeling smarter.